Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video, we're going to be exploring an example of our past video which involves determining the collision flux and deriving that particular equation, which is what you see in this particular screen right here. So we have our pressure is over all square root of 2 pi m, which is the mass, multiplied by the Boltzmann's constant, multiplied by the temperature, and we derived this equation from various interesting themes on our previous video. First, determining the number density, and then looking at how you can incorporate the specific relative mean speed to becoming the mean speed, which is what we have right here, which turns out to be 1/4 or quarters of the mean speed. And so therefore, this is then introducing our integration, which accounts for the variation or distribution of velocities towards a specific wall barrier or space wall that a particular particle is hitting against at a particular time interval. And so we are now going to be able to use these parts of the derivation process or deriving process to perform this particular question. And this question here says that a solid state or solid surface with dimensions of 3.5 millimeters by. Looking at this question here, it says that a solid surface with dimensions of 3.5 millimeters by 4 centimeters is exposed to helium gas at that particular pressure of 111 at a specific temperature, which is 1500. And now you're asked, how many collisions do helium atoms make with the surface at that particular time? So in this part here, let's have a little diagram to visualize what is going on in this particular question. And so in the diagram, we are assuming that we have a surface that is solid in nature, and we have the dimensions of this surface, and the dimensions of the surface is, in this case, we have the measurement of the width to be 3.5, and this is units to be millimeters, and while this is by 4.0 centimeters. And this measurement here for the area is going to be making the units to be equal, not only in terms of the dimensions but also the area. Therefore, our area will be in meters squared when you determine that particular combination. So this particular wall is experiencing some form of pressure by particles that are heading towards it. And the specific particle, when we actually release them into a particular space like this, is called helium. And so helium, which is pretty much a unit atom in this case, is going to be heading towards the wall, and the velocity, which is represented as v at x, which in this case, putting our coordinates, will be able to assign the unit dimensions direction to be in terms of the x. Therefore, from the time it's released to when it hits, we actually are going to assign it as changes time, and therefore we'll be able to determine our distance, which we did on our previous video. So our change in time is measured in seconds, and it is 10 seconds in this particular question. So these are the necessary information, and other information based on the givens includes the following. We have our givens, which is, first, we are given the area indirectly of the solid surface, and to determine that, first we need to convert our units. So in this case, we are getting 3.5 millimeters by 4.0 centimeters. And so to go from millimeters to meter, we are going to be getting our number in this case for 3.5 to become 3.5 times 10 to the negative 3. This is multiplied by, for centimeters to meter, it will be in this case 4.0 times 10 to the negative 2 meters. So once you have this, our answer in this case will be around 14.0 times 10 to the negative 5 meter squared. And this is actually our area for this particular surface that our particles will be colliding at. Now, the next variable that we're given in the question is the pressure, and the pressure here is, according to the standard unit, in this case is pascals 111, and then we have our other variable, which is temperature, determined or given to be 1500 kelvins, which is also one of the units that is standard for this overall equation. And then our change in time is in this case given to be 10 seconds. And next is the molecular or the atomic weight of helium. So in this case here, which we are going to determine is that, hey, we need to convert it from grams per mole to kilograms per mole. And looking at the periodic table, we notice that it is around 4.01. And so converting it to kilograms per mole, we actually multiply this by 10 to the negative 3 kilograms per mole. So once you have this, there are other standard units that we're going to come across, which includes the following. We're going to be given the gas constant, or we're going to be using it, which is 8.314, in this case, joules per mole times kelvins. And then the other one is our Boltzmann's constant, which is around 1.38 times 10 to the negative 23 joules per kelvins. So once you have all these variables assigned, we are now going to go into what is required. Now, the required here in this question is to be able to determine what the number of collisions that will be exhibited in this particular state. So the number of collisions is going to be determined, and to determine that, we need to determine what the Z is. Now, there are two types of Z. One has a subscript, which has an M, and the other Z, which is a small letter, actually is expressed as, in this case, the collision frequency, which tells us the number of particles that will be collided by one particle at a particular time period. And so, in this part, we need to then look at our analysis and figure out how to rearrange a specific equation, and from there be able to have the subject of the formula to be in terms of the collision frequency. So in this part, we know that the collision flux, which is what we derived from our previous video, is expressed as huge Z with subscript M, and this is equal to the number density multiplied by 1/4 of the mean speed. And we know that this is also equal to the collision frequency, or divided by the area multiplied by our time interval. And so once we have this taken care of, we know that since this is in this case going to be expressed as equation 1, we are going to put our equation for the mean speed, which is in this case square root of 8 RT over pi multiplied by the molecular weight. We're going to put this in equation 1. Therefore, once you put this in equation 1, we'll be able to re-express our equation, which is what we have here, in terms of these particular variables. Therefore, we are able to have our equation by focusing now on this particular part, and therefore we have our Z over area multiplied by the time interval to be equal to the number density times 1/4, and this is all multiplied by the square root of 8RT over pi molecular weight. So once we have this taken care of, our next step here is to assign this to be equation 2, and we're going to put another equation where we're going to change our number density now to a form that will show the pressure relationship with temperature, and this is actually, as the denominator will be introducing our Boltzmann's constant. Therefore, putting this in equation 2, we're going to arrive at a new equation that satisfies the question that is given, and therefore this our new equation is Z over the area multiplied by R time interval, and this is now equal to the pressure over our Boltzmann constant multiplied by temperature, all multiplied by 1/4, and we have the square root of 8RT over pi m. So once we have this new equation derived, we're going to use this equation to determine our specific collision frequency. So we're going to solve for Z, and so to solve for Z, we will have to do what? Multiply both sides by a change in time, and therefore our new equation, which is now in terms of Z, is equal to P over our Boltzmann constant multiplied by temperature, and this is going to be multiplied by 1/4. Take note that we also have our area and our time, and this is then multiplied by our square root of 8RT over pi molecular weight. So once we have this equation, we'll be able to solve for our Z by putting all our givens in this particular part in this particular expression right here. And so therefore, for our Z, we know that our pressure is going to be, let's put our area at the front. So we're going to start with area, and so our area we know is 14.0 times 10 to the -4. Take note that the unit is in meters squared, and the next one here is that it is multiplied by 10 seconds, which is our time, and then our pressure, which is our next in focus, is going to be, in this case, 111. We know that the pressure is measured in pascals, therefore pascals is measured as Newton per meter squared. So we have our Newton per meter squared, and this is divided by our specific Boltzmann constant, which is 1.38 times 10 to the -23, and we know that the unit is in joules per kelvins. Therefore joules is expressed as the Newton meter over kelvins, which is below, and then this is multiplied by our temperature, which is 1500 kelvins. And so once you have this part taken care of, our next one is to focus on the one in the bracket, which involves the square root. Therefore this inside square root will have our 8 multiplied by our gas constant, 8.314. Take note that the unit is in joules. We know that joules is in terms of kilograms meters squared, and this over seconds squared. But take note that we have our moles and we have our kelvins in there, and so this is now multiplied by the temperature, which is 1500 kelvins, and this is all divided by our pi multiplied by our specific molecular weight, in this case atomic weight of helium, and therefore we know this value in kilograms per mole to be 4.01 times 10 to the negative 3. Take note that this is in kilograms per mole. So once you have this taken care of, we are going to evaluate the unit and also evaluate the constants in all these expressions. So focusing here on the unit, we know that our meter squared is going to cancel out our meter squared. We know that in this part here, our Newton will cancel our Newton. We know that our kelvins will cancel our kelvins. And on this other side, take note that we also are missing one thing, which is our 1/4, which is what we have right here. So don't forget this 1/4. We'll need that very soon, which is what I'm going to put in between the two brackets as the multiplication process occurs. And then inside our square root, we have our grams, definitely canceling out our grams. We have our moles, canceling out our moles. We have our kelvins, canceling out our kelvins. And what we're left with in our unit inside the square root is meter squared over second squared. Therefore, in our final step, which is now having our new expression for Z, we know that this is actually going to be showing our constants in here to be 4.0 times 10 to the, in this case, we're looking at 10 to the power of negative 4 times 10 to the power of 1. In this case, it's going to be 10 to the power of 4. Take note that this here is 5. I made a mistake. It's meant to be 5, not 4. So eraser and change this to 5. So 10 to the power of 5 times 10 to the power of 1 is equal to 10 to the power of negative 4. Therefore, in this case, we have our units to be here in seconds, which is what is left. And then inside this bracket, we are multiplying this here by all. We'll multiply all this by 1/4, and then what we have is our value to be 1.34057 times 10 to the 23. Take note that the unit, 21, not 23. So 21. And our unit is in meter negative 1. And the other one now inside this particular square root is we have our value to be the square root of, in this case, 7919486.4. And take note here that our unit is in meter squared over second squared. So once you have this expressed as that, we're going to further evaluate the square root, and then from there we'll be able to analyze everything at the end. So in this part here, by re-evaluating this, we have 4.0 times 10 to the negative 4 seconds, and this is multiplied by 1.34057 times 10 to the power of 21. Take note that this is in 1/meter, and then our square root is, in this case, going to be giving our constant to be 2814. In this case, I think it's 0.158, and we have our meter squared to become meter over our second squared to be seconds. And so next is evaluating our units. Seconds cancels out our seconds, our meters cancels out our meters, and what we are left now is our Z value. Once you multiply the constant, is in this case the collision frequency, which is in this case the number of collisions that helium will experience against the wall in 10 seconds at that particular pressure, which is given the question, and temperature to be equal to 5.2816 times 10 to the power of 21, how many collisions, that is how many collisions that is going to be made during this particular process dealing with helium atoms in that particular space. So that is really a huge amount of particles in just 10 seconds that will experience collision and therefore causing an increase in pressure against the surface that is the solid surface in this particular question. So I hope you found this particular activity interesting in terms of not only getting the right formula that will be required for you to fit all the required variables, but also to be able to watch out for the units and also be able to arrange your solution in an orderly way in order for you to get to your final answer in this particular case right here. So that's about it for this video. I hope you have found this really informative. Please hit a comment down below. Let me hear your thoughts. By that way, I can talk to you soon. Stay smart as always and believe in yourselves.